Welcome to the pod, Cultivating Innovation, one batch at a time. This is biomanufacturing and fermentation technology.
Welcome back to the deep dive. Today we are focusing on something that, on the surface, sounds incredibly simple: feeding microorganisms. I mean, you think about these massive industrial biomanufacturing plants, huge bioreactors, tons of product, and it seems like the easy part should just be, adding the food.
But that's the thing, that simple task is actually one of the most complex dynamic control problems in modern engineering. The source material our listeners sent over makes it really clear we're no longer just supporting growth. We are actively trying to program the cell's every move using its food.
Okay, let's unpack that. So the sources frame this whole idea of media optimization not as some static lab recipe, but as a central quantitative control strategy. It governs everything from, say, how fast the cell's internal metabolism runs to the actual quality of the final product, and all of this while dealing with real industrial constraints.
What's really fascinating here is that shift in perspective. We've moved to a highly strain-centric and product-centric approach. We're going from, passively supporting simple growth to actively shaping the cell's internal regulatory states, controlling cofactor balance, and building in system robustness. Media composition is now an explicit design variable. It's not just a recipe anymore.
It sounds less like cooking and more like coding. So let's jump straight into that code. The first and maybe most powerful lever we have is the carbon source itself. It feels like we're using the blend of carbon, the specific fuel mix, as a kind of metabolic steering wheel to literally define which pathways the cell is even allowed to access.
That's a perfect way to put it. The chemistry of the carbon source dictates the pace of the whole system. Take Crabtree positive yeast. They're a classic example of what you could call microbial greed.
Greed? How so?
Well, if you give them a high concentration of fast-acting glucose, they just gobble it up so quickly they basically ignore the oxygen that's there and shunt the carbon into wasteful byproducts like ethanol.
So instead of using the really efficient, high-yield respiratory pathway, they're essentially just making cheap rhyme, wasting energy.
Precisely. They're prioritizing speed over efficiency. But the elegant solution the sources point to is carbon blending. There are pilot runs, validated by proteome allocation models as recently as 2025, that show by replacing some of that quick-hit glucose with the slower substrate like glycerol, you effectively slow them down.
You're forcing them to be less greedy. So what kind of gains are we talking about when you manage that pace?
The studies confirm that blending, say, roughly 30 to 50% glycerol with glucose can reduce the specific substrate uptake by 15 to 25%.
Okay, and crucially, what does that do to the yield?
It forces that carbon into the efficient respiratory pathway. So you end up increasing the final biomass yield by about 20%. That's a massive economic gain just from changing the fuel mix.
Speaking of waste, the classic villain in industrial fermentation is overflow metabolism, especially in E. coli. When they feast on high glucose, they produce acetate, which is toxic. It inhibits the product, and it's a huge carbon loss.
It really is the #1 bottleneck in so many E. coli bioprocesses. I mean, high glucose, even with oxygen, can divert anywhere from 20 to 40% of your useful carbons straight into acetate.
So how do we stop that?
Well, this is where tools like Flux balance analysis, or FBA, come in. The models tell us the critical control strategy is just constraining the carbon uptake rate.
Is there a quantified sweet spot we're aiming for, a kind of speed limit?
There absolutely is. FBA really delivers a clear mandate here. You have to maintain a very tight, low cap on the specific glucose uptake rates. We call it $22. And you need to keep that TULRs below roughly 0.8 to 1.2 grams per gram of dry cell weight per hour. By capping that rate, you prevent the cell from gulping and wasting that 20 to 40% of carbon.
So slow and steady feeding, not just dumping it all in at once.
Exactly. But it's not just about the carbon feed rate. We also have to manage the cell's internal energy balance, the redox cofactors.
The internal batteries and wiring.
That's right. And we specifically look at the NADH to NAD+ ratio. This ratio controls fundamental steps in both energy and biosynthesis.
That's a fascinating analogy. It's like tuning the internal engine with a specific fuel additive.
It is. The sources show that introducing co-substrates, like formate, for example, has been shown to maintain that NADH-NAD+ ratio at a very specific optimized level, right around 0.06. And that subtle tweak helps the cell run cleaner. It can improve overall carbon efficiency by 25 to 35% in large-scale fermentations.
Okay, so let's say the goal isn't just a healthy, waste-free engine, but actually producing the product. We need to switch gears. We need to tell the cell, stop multiplying, start manufacturing. How do we send that signal?
We use the carbon to nitrogen ratio, the C to N ratio. This is, the central lever for decoupling growth from production.
How does that work?
Well, high nitrogen tells the cell, build more walls, divide, multiply. But when you limit the nitrogen and you keep the carbon abundant, you send a different message. You're saying, stop building new cells, but you still have plenty of energy, so you have to start storing it or producing something with it.
So you're forcing resource allocation. What does that look like in practice?
In hosts that are designed to produce storage polymers, like, say, certain Pseudomonas strains that make bioplastics like PHA, a high C to N ratio is essential. We're talking 20 to 30 molar. That nitrogen limitation drives the cell to store all that excess carbon as PHA. You can see it accumulate to really high fractions, sometimes 60 to 80% of the cell's dry weight.
You're basically turning the cell into a tiny storage locker.
Precisely. But conversely, if your goal is to secrete a high-value protein or an enzyme, the opposite might be true. That whole process making, folding, and secreting large proteins, it's extremely taxing on the cell. It creates what we call a proteomic burden.
The internal machinery is just overloaded.
Exactly. So in fungal enzyme secretion platforms, the sources highlight that generous amino-nitrogen supplementation is actually what's required. It relieves that burden. 2024 trials even showed this kind of supplementation boosted product titers by a solid 20%.
Okay, we've covered the big drivers, carbon kinetics, redox balance, and the CN ratio. But industrial processes aren't just about the major stuff. And here's where it gets really interesting, right? The hidden rate limiters. The micronutrients.
This is where that shift from complex, sort of ill-defined media to chemically defined media really pays off, because a defined media lets you see the bottlenecks that were masked before by, random trace ingredients. We're talking about vitamins, trace metals, and osmolytes that define these hidden rate-limiting steps, especially in the really extreme environment of a high cell density culture.
And the sources heavily emphasize that the chemistry of how you deliver them matters. It's not just that iron is present, it's about how it gets to the cell.
Correct. We call this speciation. If you just dump metal ions into a tank full of chemicals, they often precipitate out, especially at high pH. The metal might be in the tank, but it's chemically unavailable. It's just a lump at the bottom.
So you need to give the metal a kind of bioavailable postal code.
Exactly. Optimizing metal speciation and chelation, for instance, using controlled delivery of iron, maybe complexed with organic acids, prevents that precipitation. It keeps it bioavailable. And we've seen incredible results from this. There are reported 20 to 25% tighter gains in some organic acid processes simply by perfecting how you deliver trace metals. That's a huge yield increase from something that used to be considered background noise.
Now let's look beyond just growth factors. Media is also being actively used to program the cell's stress tolerance. It's like you're pre-arming the cell against the harsh conditions inside the bioreactor.
Stress management is absolutely critical for viability, and one of the biggest stressors is osmolarity. Concentrated feed solutions often drive the culture way beyond physiological norms. We're talking hundreds of milliosmoles per kilogram.
And that takes energy to deal with. Energy that could be going to the product.
So we can bypass that energy cost. Targeted supplementation with established osmoprotectants, like betaine, that improves cell viability and stress tolerance a lot in high-density cultures. And we can also use media to boost the cell's oxidative defense. High metabolic rates, high oxygen transfer. They inevitably drive the formation of reactive oxygen species, or ROS.
The cell is running so fast, it's effectively burning itself out.
To combat that, we look at supplementing media with redox active micronutrients, things like selenium, which is essential for certain enzyme cofactors. By enhancing the cell's internal glutathione defenses through the media, we keep that cellular engine running clean and stable for longer.
And this all leads to the ultimate metric, which is product quality. The media choices you make at the very start, in the tank, directly impact the purity and the structure of the final product, which of course hugely affects downstream processing and cost. If the product is messy coming out of the reactor, the cleanup is going to be expensive.
Absolutely. The downstream cost can be a huge fraction of the total manufacturing expense. We see this acutely in mammalian systems that produce high-value antibodies. Meaty components like glutamine often break down into byproducts, lactate and ammonia.
And those byproducts aren't just waste, they're active saboteurs, aren't they?
They are. Those toxic byproducts negatively affect crucial product quality attributes, specifically the glycosylation patterns on the antibody. If the sugar chains are wrong, the drug might not work. And that failure point, driven by media choices, is why the industry is seeing this massive shift towards developing complex, glutamine-free media formulations.
So the product quality problem really starts upstream, in the feeding strategy, not just in purification.
It does. And in microbial systems, we use media for structural control as well. We are actively promoting the correct assembly of the product. Specific ions, like zinc or magnesium, are carefully added to the media to help promote the correct folding and assembly of complex proteins. By controlling that folding inside the reactor, you minimize aggregation and you radically reduce the purification burden downstream.
That level of integration, connecting a trace ion in the media to the final structural integrity of the product, that is the core of this whole modern approach. Now let's tackle the real world, because laboratory perfection rarely survives contact with industrial scale, and the biggest challenge in scaling up is heterogeneity.
This is where physics just creates havoc. In a vessel that's over, say, 10 cubic meters, mixing times can stretch to tens of seconds, and that creates significant spatial gradients. So the cells near the feed inlet get this intense burst of high substrate, a feast, and then as they circulate away, they quickly run out of food, a famine.
This feast-famine cycling sounds catastrophic for a finely tuned process.
It is. It's a massive stressor that forces the cell right back into those wasteful overflow metabolic modes we were trying to prevent, driving up local byproduct formation.
So how does media design solve a mechanical mixing problem? That's the core question.
We use the uptake kinetics we already optimized. Instead of using pure, fast uptake glucose, we intentionally use slower uptake carbon sources, maybe disaccharides or even polymeric sugars that the cell has to break down first. If the cell physically can't gulp down the substrate too fast, it dampens those local uptake spikes, and that mitigates byproduct formation across the whole reactor.
So the media itself acts as a kind of slow-release mechanism to buffer the physical gradients in the tank. That's clever. We also have to talk about phenotype stability. You've engineered this perfect strain, but over a long production campaign, you need to make sure it maintains its high-performance characteristics.
And media is absolutely critical for maintaining that selection pressure, especially now that we're moving away from using antibiotics in manufacturing. We use what are called nutrient-based selectors or auxotrophic selectors, integrated right into the media to maintain plasmids or synthetic constructs.
So instead of a harsh antibiotic hammer, you're using a nutrient leash.
Exactly. If the cell loses the plasmid, it also loses the ability to make an essential nutrient for itself. And the media we design simply starves that specific cell line out. It's a very elegant solution.
And it works over the long term.
Oh, yeah. When dosed correctly, these selectors have shown very high retention over many, many generations. It's a robust, non-antibiotic strategy for maintaining phenotype stability.
This level of control just seems impossible without advanced computational support. So this brings us to modeling and data. This is where media optimization becomes true predictive engineering.
The quantitative backbone here is dynamic FBA Flux balance analysis and another tool, 13C MFA, which is a sophisticated metabolic fingerprinting tool. These tools integrate the changing concentrations in the tank with the cell's known metabolic networks, and they predict exactly how a specific feed trajectory will reshape the flux map over time.
So you're not guessing. You're dynamically mapping the cell's internal operations based on your external input plan.
Precisely. And the models are delivering. FBA, coupled with smart media design, has been applied to high-performance enzyme producers like Bacillus, and it's successfully predicted flux redirections of up to 30% into the final product pathways. And that was validated at pilot scale.
That's powerful.
It is. And on top of that, we are seeing emerging tools like Bayesian optimization and reinforcement learning being used to search these huge formulation and feeding spaces much more efficiently.
They're essentially learning the optimal complex feeding strategy over time, leveraging digital twins of the process.
Right. It moves optimization from tedious manual experimentation to targeted, rapid-fire predictive searches.
So finally, let's connect all this back to industrial philosophy and regulation. Specifically, quality by design, or QBD. This whole effort isn't just about finding the best operating point, is it? It's about finding the most resilient one.
That concept of resilience is absolutely key. Industrial practice is shifting from seeking a single knife-edge optimum recipe to defining robust media windows. These are ranges for your C to N ratio, for osmolarity, for metal levels, where performance is resilient to the, inevitable variability in your raw materials.
So if your raw sugar feed varies by, say, a few percent in its trace nitrogen content, your overall output doesn't just crash.
Exactly. You have to build in that tolerance. The sources cite things like requiring a plus or minus 10% variation tolerance in the feed. Media design is increasingly seen as an adjustable risk management layer. And global regulatory guidances like ICH Q14 now emphasize control strategies for critical raw materials, formally recognizing media as a key part of robust manufacturing.
That makes perfect sense. The control starts with the inputs, and the predictability starts with the programming.
If we really connect this to the bigger picture, media is no longer just a recipe, it's the operating system for the cell. By tuning carbon blending, C-to-N dynamics, and micronutrient profiles, we're explicitly programming resource allocation to achieve scalable excellence. We're bridging mechanistic biology with manufacturing resilience.
So what does this all mean for you, the learner?
Well, media optimization has evolved into a highly advanced, model-supported, and constraint-aware field. It ensures consistent productivity and quality in these massive bioreactors, despite all the real-world constraints like scale and supply fluctuations. It's really the silent core of predictive biomanufacturing. And here is a final provocative thought for you to consider. We've seen how essential it is to specify and control for specific inhibitor fingerprints in, say, sustainable waste-derived feedstocks. For example, you might need to require that phenolics are below 50 milligrams per liter in a citric acid process to preserve stability. So how might this critical requirement for media stability drive innovation not just in fermentation technology itself, but also in the entire upstream chemical processing and purification of those sustainable waste-derived feedstocks? That necessity of an ultra-clean feed could reshape the entire supply chain.
How do we solve the valley of death in biomanufacturing? It starts with better data and more robust fermentation technology. Join us on Biomanufacturing and Fermentation Technology by Prasad Ornala for our upcoming series featuring lead researchers and process engineers. We're discussing everything from bioreactor design to downstream processing, DSP efficiency. Follow us now to join the conversation on the technical frontiers of biology.